right, so picking up where we left off on continuous functions, a few more things to say that weren't in the previous video. If we have a function between metric spaces, we had a very nice characterization of what it meant for that function to be continuous, right? F is continuous means this open set formulation. If U is a open subset of the codomain, then its preimage, you see in the graphics, its preimage as a subset of M is open in the domain. If you take the preimage of an open set in the codomain, you get an open set in the domain. This is an extremely smooth way of phrasing continuity. For instance, suppose you had a situation of composition of functions, right? If you compose two continuous functions, the result should be continuous. So if you had M mapping to N via F, N mapping to L via G, if F was continuous and G was continuous, you would expect that the composition G composed with F should be continuous. It is, and the proof is really, really quick with open sets. What it means for this function to be continuous is the preimage of every open set in L is open in M. Watch how the argument goes. Suppose U is an open set in the codomain. Well, G is continuous, so the preimage of that, G inverse of U, is then open. And that's a set in N. Well, now I've got an open set in N. F is continuous. The preimage of that set in M is open. F inverse of G inverse of U is open in M. But if you remember your rules of functions, F inverse of G inverse of something is exactly G composed with F inverse of the set U. The end. Okay? Open sets pull back to open sets by G because it's continuous, which pull back to open sets by F because it's continuous. That's the preimage of the original open set under G composed with F. So composition of continuous functions are continuous. Pretty nice. There's a few other things we want to say about continuity. I want to learn how to build continuous functions. And there's a few little tidbits we have to say before we do that. The first remark is this. Addition, subtraction, multiplication, max and min are operations that take two real numbers and spit out a real number. In other words, these are functions from the real line cross the real line, kind of like a metric does. It takes two numbers in and spits one number out. So the sort of function is the same. This function would say, given a point x, y, give x plus y, given x and y, make x minus y, x times y, the maximum of x and y, or the minimum of x and y. It's not hard to prove. These are all continuous. Okay? The proofs are really easy for plus, minus, max, and min. The proof for multiplication has a little bit of complicated algebra, but the logic is very straightforward. We also have an operation of division, which you can't divide by 0, so it's technically a function from r cross the real line minus the element 0. So the first number could be anything. The second number could be anything except for 0, and spits out a real number. That's also continuous. Okay, so addition, subtraction, multiplication, max, min, and division are all continuous functions on the appropriate domains. You may not have thought about addition as a function of two operands. Maybe you took abstract algebra and saw it this way. Maybe you haven't thought about addition itself being a continuous function, but it is. You can prove it with the definition. If you want to talk about building continuous functions, though, you need one more operation that you probably didn't talk about anywhere. I'm going to talk about it just for real numbers. That's where I care about it. No, I'll talk about it in general. If you have two functions between metric spaces. Now, most of the time, these metric spaces are going to be real numbers. Sometimes not. So I'm going to define it generally. M has a metric, N has a metric. There's a stacking of these functions we can build. I'm going to draw it with a box. F box G is going to be a function. Now, each element of M F sends to an element of n and G sends to an element of n. They're two different functions. To stack them up, what I'm going to do is make a function from m to n cross n. So for every element of m, I'm going to get a pair of elements of n, and it might be obvious what my pair is going to be. What's the rule? An element x in m, I'm going to take f of x in the first coordinate and g of x in the second coordinate. So all this function does, it takes two functions from m to n and stacks them together into a function from m to n cross n, which gives you a pair of outputs. It uses f for the first one and g for the second one. How's this useful? Well, this is also, you might guess, continuous. Okay? If f and g are continuous, of course. If you start with two continuous functions, their stacking will also be continuous. So adding, subtracting, multiplying, dividing, max, min, and the stacking are all continuous operations. All right? So what this allows us to do is really gives us all the tools we need to see and justify, once you've proven those basic results, what functions are continuous. A large class of functions that are continuous. For instance, on the real line, every polynomial function is continuous. Why is that? Well, constant functions are continuous. That's a really easy proof. Given the epsilon, take any delta you like. Okay? Identity function is continuous. Identity function meaning x maps to x, right? That's also continuous. Take delta equals epsilon, right? Write out the definition of the identity function. Delta equals epsilon works. Once you're there, this is, so to speak, your constants. This is, so to speak, your x. You can quickly see that any polynomial must be continuous from the stuff we said before. So you know polynomials are continuous from calc. You could sort of take a higher view of this. Why is x cubed minus 2x, right? Technically the function x maps to x cubed minus 2x a continuous function. Break it into pieces from what we've seen how to do. This function we construct as take the identity function, multiply it by the identity function, which is then continuous, multiply by the identity function again, which is again continuous, take the constant function 2, multiply it by the identity function, which is continuous, and subtract. This rule can be built from addition, subtraction, multiplication, division, etc. by the operation we've seen, preserve continuous functions. So the main point of this is polynomials are continuous functions. Okay, they're the easiest functions we know in the real line, and we're going to be talking more about them later. If you want to send a complicated function in terms of simple functions, polynomials are a great place to look. These polynomials are a special case of something that's going to be important later on. So if M is a metric space, right, with some metric, C of M is the continuous real valued functions on M. If you like, it's the set of all functions from M to R, so real valued functions that are continuous. Okay? This is for any metric space, how can you map it into the real line continuously? M could be the real line, M could be the plane, M could be some more complicated space. Some points about this. If you have two continuous functions in C of M, I could scale that function. It would still be continuous. Right? I could also add the functions. That would be continuous. I could also subtract the functions. It would be continuous. If you have a set of objects that you can scale, add, and subtract, that means this set C of M is a vector space. You can check all the axioms. The set of continuous functions, you may have seen this in linear algebra, the set of continuous functions on any metric space forms a vector space I can scale and add. Okay, because they're real valued functions, I can do something you didn't see in linear algebra. I can also multiply the two functions. That's a multiplication. If f and g are continuous, f times g will be continuous. When you've got a vector space where you can also multiply elements, which you didn't talk about in linear algebra, I expect, that makes of your set what's called an algebra. Okay? So being an algebra subsumes being a vector space. So the set of continuous functions, not just a set, it's a vector space. It's not just a vector space, it's an algebra. It's also not just an algebra. There's another operation you can do which keys off of the things I talked about earlier. You can take the maximum or minimum of two functions, and if they're continuous, the max or min of those two will also be continuous. Right? Just to be clear, what do I mean by the max or min of two functions? Here's the real valued case. Here's the squaring function. Here's the function, constant function 1. The max of these two functions is just point-wise which function is bigger. It's here, here, here. The constant function and the squaring function are continuous. The max will be continuous. What's the min of the two functions? It's the smaller of the two values for each point. So it's here, here, here. That's also continuous. So there's more things you can do with continuous functions than you might realize. You can add them, subtract them, multiply them. You can't divide them unless you make sure you're not dividing by zeros. That's not something we're going to talk about. You also take the minimum and maximum of two functions. The result of two continuous functions, max and min, will be continuous as well via the stuff we introduced earlier. This makes C of m what's called a lattice. Right? A lattice is a space where you can take two functions and find their min, so to speak, or find their max. It's called meet and join or something. We will see C of m later. Continuous functions, continuous real valued function on a metric space is a vector space, it's an algebra, and it's a lattice. All of these things are going to be important later on. Right? One more thing about continuous functions. Suppose we got a function from the real line to the real line. There's something we're going to talk about soon, and it's going to be kind of subtle, so I wouldn't introduce it now. We could define the set D of f to be the set of points in the domain where f is discontinuous. That's what the D is, okay? F is discontinuous at x. Okay? We will have more to say about this soon. But before we get there, I want to observe some stuff we've seen about sets of points of discontinuity for real valued functions. What is possible for the set of discontinuities? Well, back in chapter, I think it was 1 or 2, I can't remember, we've seen some examples. Well, first of all, we've seen D of f could be empty. Now think this through carefully. D of f is the set of points where f is discontinuous. D of f being empty means your function is continuous everywhere, right? For example, any polynomial. There are lots of functions that are continuous on the whole real line. Those are great functions. We've also seen examples of functions that aren't so well behaved. We saw this function that's 1 on the rationals and 0 on the irrationals. For that case, the set of discontinuities is the entire real line. That function is discontinuous nowhere. Right? That was an exercise in an earlier chapter. We also saw this other function. Oh boy. Well, I'll say it is the soup of 1 over n chi 1 over nz or something. Doesn't matter how you say it. This function that took the integers to 1, the half integers to a half, the third of integers to a third, etc. That one was a much more difficult function. Its set of discontinuities was the rationals. It was discontinuous at the rationals, continuous at the irrationals. Okay? I just want to start collecting these. You also saw some examples back in earlier chapters. You could have the set of discontinuities be a single point, or 2 points, or 5 points, or the integers. Okay? If we collect all these together, what are things we've seen for the set D of f? Function we've experienced already. D of f could be empty, it could be the whole real line, it could be the rationals, it could be a single set of singleton, it could be a finite set, it could be the integers, say. There are certain sets we've seen come up as set of points where a function is discontinuous. It's a legitimate question, one we're going to get into later. What can we say about the set of discontinuities for a real value function on the real line? we'll have a classification theorem that says exactly what's possible. I will just point this out. You might ask, the empty set, the integers are a finite set, the rationals, the real line. What about the irrationals? Well, that's not a cube. Could we get a function that's discontinuous just at the irrationals? Lots of stuff's possible, right? We can get a function discontinuous just at the rationals. Can we get a function discontinuous just at the irrationals? Don't try, because we can't. It takes a fair bit of work to prove it, but it's an interesting result. It's impossible to have any function on the real line that's discontinuous only at the irrationals. It could be just discontinuous at the rationals. It could be just discontinuous at every point of the real line or no points at all. There are lots of things that are possible for D of F. There are a few that aren't, especially, key fact, you can't have a function that's discontinuous just at the irrationals. I'll leave it at that for now, I think, for the continuous functions. There's a bit on the distance function, comes up in a problem. There's a bit on the sheet about homeomorphisms, isometries. We will talk about these when we need to, but I think they're not essential yet, and we're short a bit of time. So what do we have? All your stuff from continuity in the previous video. We have ways to build continuous functions, add, subtract, multiply, divide, max and min. We have C of M as a lattice algebra. Set of all continuous functions on a metric space. Real valued functions is a very full-featured set. And finally, just a lead-in for some later things. A real valued function, we can define its set of discontinuities, points to the domain where it's discontinuous. We've seen lots of examples, but we're going to see that certain things are impossible for the set of discontinuities.